Hello, my name is Sarah Chestnut, and today I'm going to tell you about my experience working as an intern through the RuralWorks program this summer. First, here is a little about me. Again, my name is Sarah Chestnut. I'm from Clayton, North Carolina. I studied at Johnston Community College and received my Associate in Engineering degree in 2021. I'm about to enter my final year at NC State, so I will receive my Bachelor of Science in Industrial Engineering degree in May. Once I graduate, I am planning to stay local and work as an industrial engineer in manufacturing. This summer, I interned at AAF Flanders. AAF Flanders is responsible for the manufacture of residential, commercial, and industrial air filters. Their clients include Walmart and Ace Hardware. AAF Flanders is working to bring clean air to life, as their slogan says. They are located in Smithfield, North Carolina. I was hired as an engineering intern working in continuous improvement. My supervisor assigned me to the new Helios lines. These two machines, called Helios 3 and 4, arrived in February and were supposed to be producing 4,000 to 5,000 filters a day. However, they were consistently not meeting those production goals. I was to define the process flow, identify the process parameters, determine the fault and stop rates, and create the troubleshooting guide. The first step was to learn the process well. Over the course of the internship, I spent over 200 hours simply observing the lines, learning from operators, and collecting data. I wanted to understand the process well and encourage confidence in my statistics. I created 2 diagrams to illustrate the process flow. The first diagram on the left follows one filter being made from start to finish. It includes all the steps that one filter goes through, and I included the average times of the critical steps. This diagram was important because it helped me identify all the important steps, which I later investigated as process parameters. The second diagram on the right shows the 4 stations on the machine from a bird's eye view. 4 filters are worked on at once. Each station completes their part of the filter before the carousel spins to the next station. The bottom of the filter is formed at station number 1. The filling of the filter, called the media, is placed into the formed bottom at station number 2. At station number 3, the top of the filter is flipped on top. At station number 4, the top is formed onto the filter and the filter is finished and pushed inside the tower. This diagram was important because it helped me to see which station was the critical path, or which station the carousel has to wait on before it can spin. Once I had a good grasp of the process, I identified 33 critical process parameters. 25 of those were timed parameters, meaning that I had to time the steps using my stopwatch. For the timed parameters, I collected 300 observations for each. I collected 150 from Helios 3 and 150 from Helios 4. The more data points I collected, the closer I was going to be to the true statistics. I also explicitly defined each parameter by listing exactly when I started and stopped the clock when making my observations. This enabled me to keep track of exactly how I got my numbers. Once I completed my observations, I evaluated the data to find the minimum, mean, and maximum. In my evaluations, I used the data to compare the 2 lines and find differences in how they ran. I found the largest and smallest differences between the 2 lines, and I used graphs to showcase the differences between Helios 3 and 4. In the graph shown, you can see that on average, Helios 4 takes longer to move the bottom piece of the filter into the former than Helios 3. When looking at the data across both lines together, I found the parameters that had the largest and smallest ranges between their minimum and maximum values to prove which parameters vary significantly and which don't. I also found the parameters with the longest and shortest average times. In the chart, you can see the top 5 parameters with the longest average times. The time spent inside the tower parameter takes 3.4 minutes on average. Once I completed my evaluations for the process parameters, I had to find how often the machine faults and stops per hour. I defined a fault as whenever the machine automatically quits running because something went wrong in the process. A stop was defined as whenever the operator stops the machine because they see something wrong that could cause a fault later, such as glue buildup. I organized the faults into general groups based on which station they occurred at. I collected 87 observations, 50 from Helios 4 and 37 from Helios 3. I had planned to collect 50 from both, but ran out of time. Fortunately, it was still enough observations for the data to be statistically sound. I then found the minimum, mean, and maximum number of faults per hour. Similar to my work for the process parameters, I compared the rates between the two lines and found the largest and smallest differences between them. In the chart on the left, you can see the top 5 parameters that had the largest differences in rates. The bottom not forming or loading correctly fault at station number 1 occurred significantly more often on Helios 4. When looking at the data from both lines simultaneously, I found the faults that had the largest and smallest range and the faults that occurred the most and the least often. In the chart on the right, you can see that the bottom not forming or loading correctly at station number 1 happened at a rate of 2.8 times per hour across both lines. This data was useful because it showed which faults are responsible for the most downtime. My final part of the Helios project was to create a troubleshooting guide. I organized it based on my rate study to address all the faults I observed. For each group in the troubleshooting guide, I listed the group name, where the group of faults may occur at on the machine, the context of the fault and the different ways it can be manifested, and a chart of the possible causes and solutions. I also added instructions that detailed how I fixed issues with the control screen, called the HMI, for future reference. I discovered that both machines did not show the correct times, and they were not set up to show data for the shifts employed. Once I fixed those issues, I also created instructions on how to use the help screen on the HMI so that when an uncommon fault occurs that may not be listed in the troubleshooting guide, the operators can find some help with it. One of the things that I learned in this internship was to be as detailed as possible. My supervisor had me write daily summaries, which served as useful records for us both. I also learned to timestamp my observations so I could quickly report when I observed certain data points and what happened that day to explain the data points. Being detailed made me confident in my work as I could prove everything and back up all my work. My proudest moment was when I finished my observations for the process parameters and the fault and stop rates. I created a large Excel file to keep all my data and calculations, and seeing it done with its hundreds of observations was satisfying. I really enjoyed my time at AAF Flanders. They have an excellent work environment, and I have no doubt that my data will be useful to them. I'm so grateful to have had this opportunity and learning experience. Thank you for supporting the RuralWorks program.